Okay, so let's do question number 2. What are the steps involved in calculating the empirical formula of a compound? So I'm gonna do like a sample, example, and I'm just gonna do an example of how you would calculate an empirical formula, and then I'll also like talk about the different steps. So I'll write down the steps first. Basically, step 1, you want to find the moles of each element. Step 2, you want to divide by your smallest mole value. Step 3, so that when it's in its smallest mole value form, you want to make sure everything is in whole numbers. So you want to convert to whole numbers. So this will make more sense when I do an example at the bottom. So I'm going to do an example with ethyl butyrate. So basically when they give you an empirical formula question, they give you like the mass of the total compound, and then they also give you like the mass of carbon dioxide or water that was expelled when this compound was combusted. For example, they'll give the mass of ethyl butyrate. Like let's say it is 2.78 times 10 to the negative 3 grams. And they'll give you the mass of carbon dioxide and also the mass of water. So let's say the mass of carbon dioxide was equal to 6.32 times 10 to the negative 3 grams. Step 1 says to find the moles of each element. So I'm going to find the number of moles of carbon, of the carbon dioxide. And to do that, we divide by its molar mass, which is 44 grams per mole, to get number of moles, which is 1.4 times 10 to the negative 4 moles of CO2. And then to find out how many moles of each element, since there is 1 mole of carbon for every mole of CO2, that's how you would find the moles of carbon. And then to find the mass of carbon, I'm going to multiply by its atomic mass to get a final value of 1.72 times 10 to the negative 3 grams of carbon. So let's do the same thing with the water. So let's say they give you a mass of water that was expelled during the combustion, and they give you like 2.58 times 10 to the negative grams. You would divide by water's molar mass, which is 18 grams per mole, to get the number of moles of water, which is also 1.4 times 10 to the negative 4 moles of water. To find out the moles of hydrogen, there are 2 moles of hydrogen in every 1 mole of water. And then to find out the mass of hydrogen, I'm going to multiply hydrogen's molar mass, and then I get 2.9 times 10 to the negative 4 grams of hydrogen. To find the mass of oxygen that's left over, let me use a different color. Find the mass of oxygen. It's going to be our total mass, which is the 2.78 times 10 to the negative 3. And then I'm going to minus the grams of carbon and hydrogen that we found in the first part of the question. So basically, this is because we know that this compound only contains carbon, hydrogen, and oxygen. We can do this part. And you get 7.7 times 10 to the negative 4 grams of oxygen. So next, I am just going to find the moles of each element. So the first part was asking, I found all the different masses, so now I'm actually just going to find the moles of each atom. So for carbon, it was 1.72 times 10 to the negative 3 grams. I'm going to divide it by the molar mass of carbon, which is 12 grams per mole, and I get 1.43 times 10 to the negative 4 mole of carbon. For hydrogen, it's 2.9 times 10 to the negative 4 grams over 1.01 grams per mole. And we get 2.87 times 10 to the negative 4 moles of hydrogen. And then I'm going to do oxygen on the next page. For oxygen, we had 7.7 times 10 to the negative 4 grams oxygen divided by its molar mass, which is 16 grams per mole. And you get 4.81 times 10 to the negative 5 moles of oxygen. So now I'm going to write out the empirical formula just by using these mole values that we found. So for carbon, it was the 1.43 times 10 to the negative 4. For hydrogen, it was 2.87 times 10 to the negative 4. And then for oxygen, it is 4.81 times 10 to the negative 5. So since the smallest value here is the oxygen, we are going to divide all these values by the smallest mole value. So that was step 2 in the steps. And this gives us C3H6O. So since everything is already in whole values, this would be your empirical formula. So let's see what our junior tutor said. In definition, the empirical formula gives us an idea of the ratio of the relative atoms in the compound. For example, H2O only contains 2 atoms of hydrogen and 1 atom of oxygen. We can also interpret it as 1 mole of H2O contains 2 mole of hydrogen and 1 mole of oxygen. So this is if you don't have any mass and you need to calculate an empirical formula, you can assume 100 grams of a sample of the compound, and that's an easy way to convert from percentage to grams. So like what they said, using the element's molar mass, convert the grams of each element to moles. Convert the resulting moles to a whole number ratio by dividing the moles of each element by whichever the mole from step 2 is the smallest. So this is similar to our example. We divided it by oxygen's moles. After converting, the empirical formula can be written with the moles as the subscript of each element. In other cases, 1 or more moles from step 3 will not be converted to whole numbers. Multiply each of the moles by the smallest whole number that will convert each into a whole number. And then you can find out your empirical formula. So they have an example of their own. They say an unknown compound contains 69.94% iron and 30.06% oxygen. Find the empirical formula. So this is when you would convert by assuming 100 grams of the sample, we can convert the percentage to grams. And then they found the number of moles of each element divided by the smallest value obtained. So for iron, that was the smallest amount of moles, so you get 1. For oxygen, when you divide 1.87 by 1.25, you get 1.5. So you can see that there's a decimal involved. So that's why we need to multiply both by 2 to convert it to a whole number. So they get an empirical formula of Fe2O3. So this solution is correct.